the application exercise for last time. So thank you all for being flexible. I'm sorry I couldn't be here on Tuesday. My daughter was sick, and then my husband ended up getting called for jury duty. My daughter is better, but my husband is still on a jury. It's actually kind of terrible. He's like, they've had one witness, and there are 12 witnesses, and today is day 3. So I'm really hoping that the rest of them go faster. But anyways, so thank you for your flexibility. I appreciate it. So last time, first of all, on the application exercises, the first thing you were to do was to do this little bit of a leaf measurement, which I'm actually kind of excited that we were able to find class time for this, because I think hopefully this is going to help drive home some concepts that I think are actually kind of challenging in statistics, in particular thinking about confidence intervals. So that's what we're going to spend some time on today. So hopefully you've been able to share those links with me. The second thing you all did was you went to this little Shiny application, which is basically it's a little web application that I built using R to try to drive home kind of what is actually happening under the hood when we're talking about simple linear regression or ordinary least squares. Those are synonymous. And so the reason why it's called least squares is because you're trying to, the whole point of simple linear regression mathematically, the way it works, is it minimizes the sum of these squared errors. And so this application was intended to sort of give you a little bit more kind of tactile insight into what's happening here. So I had these 10 little orange data points, and I had this random line that was drawn here, and you could drag the little circle to kind of change the slope of the line, as well as drag this circle over here to change the intercept of the line. And you notice as I'm changing those, the equation down here is updating accordingly. And so what this is sort of meant to do is to give you some sense for kind of what is happening under the hood when we're doing simple linear regression. So each of these, basically mathematically what simple linear regression does is it minimizes the sum of the area of all of these little squares here. And so if you try to sort of, without putting it in R, if you try to just do it yourself, you could maybe guess what the right line was. If you could, the way you would know that you had the right line would be, one, that you would have the smallest possible sum of the squared errors here, and 2, that you would basically, the sum of the residuals would be 0. So that would mean that you sort of picked a line that fell kind of right on average, right between all of these points. And so the point of this is sort of to drive home what the big picture is for least squares, what it's actually trying to do. So something around here I think was around where you could get a pretty good estimate of that. All right, so then for part 3, you used a new data set in R. So I'm going to go ahead and go to this. So if we go back to our website, we can click on RStudio Pro. And you can create this, make sure that you're in the right project. So I'll give you all a second to get there. We're in the Apex 07 project. You were able to do that by doing new project, version control. Don't do this again if you've already done it, because it'll copy an empty one. We want to use the one that you used in class on Tuesday, but this would be, if you weren't able to pull it in, that would be how you did it. And so if I open this apex07.qmd, I can pull up kind of what we were doing. So the first thing that you'll need to do once you open this file will be to load the packages as well as the data. And so for this, we're loading the tidyverse package like we usually do, and then I'm also loading the stat2 data package. And we're going to use this a couple times in class. This is actually the R package that comes with your book. And for this particular package, so the data sets that load with the tidyverse package, they use something called lazy loading. They basically load automatically. So the Star Wars data we were able to just use once we loaded the tidyverse package. The data in the stat2 data package, you have to use this data function in order to call the data to then be able to use it. So that's what we're doing here. And so once I run that, I see this Porsche price data up here in my environment, which lets me know that I can now use it. And so if I wanted to look at this data in the console, what would I do? Yeah, question mark, Porsche price. And so this tells me that this is a data set of Porsche prices for cars that were on sale on an internet site. And it has 30 observations and 3 variables. The variables are the price, the asking price for the car in thousands, the age of the car, and the mileage, the previous miles that were driven in thousands. All right, so the first thing that I asked you to do was fit a linear model predicting price from mileage. Can somebody tell me how to do that in R? What function would I use if I want to fit a simple linear model? LM, yeah. And then what would be my outcome? Price, yeah. And then my predictor is going to be mileage. And then what do I put next? Data equals Porsche price, exactly. All right, so if I run this, I can see my output here. It shows my intercept and my slope. And so what is the beta hat 0 value for this particular data set? Yeah, 71.09. And what does that mean? How would I interpret it in the context of this data? Yeah.
No miles in the car, that's how much it would cost.
Yeah, so if there were 0 miles on a car, the Porsche is expected to cost $71,000 or $71,090. Yeah. Okay, and what is my beta hat 1 in this case? Negative 0.589, and how would you interpret that in the context of this data?
The unit decrease if mileage when the price increases.
Yes, so if for every 1,000 miles that the car has been driven, we would expect the price to decrease by $589.40. So the pieces of that are important, like if you were doing this for like a check-in or a midterm or a lab, the pieces I would want to make sure that you said if you were describing or interpreting that would be, one, you'd want to make sure you note the units. And so we know that each unit in this particular data set for mileage is the previous miles driven in the thousands. So we would say for every 1,000 increase in miles on the car, we would expect, so the first part that's important is mentioning the units for the x variable. The second is to make sure that you are saying something that indicates that the y value you're seeing is like an average or an expectation. It's not like for every single point. So we would say like the expected price or the average price would be, and then you would state what this is and make sure you also state the units for the y variable. So in this case, price is in thousands, and so we could say that for every 1,000 increase in miles driven, the expected price for the Porsche is going to decrease by $589.40. Are there any questions about that? If I wanted to save this output, so when I run this code, it will output the answer here in the console, but it doesn't actually save it anywhere. If I wanted to save this as an object that I could then use later, what would I do? Yes, I could create a variable. How would I do that?
Any name and then make an arrow to the...
Yes, you could call it anything. So I could call it model, for example, or my model, or I could call it anything I want here. So I'm going to call it my model, for example. And then I use this little arrow. And that will output the information from this model into an object called my model. And now I see that up here in my environment, so I have saved it, which is handy because then I can use it later, like if I wanted to summarize it, or if I wanted to pull out the fitted values or those y values, or if I wanted to pull out the residuals or things like that. All right, I'm going to add a little label to this chunk here. I'm going to call this LM. And now, whoops. So the next thing I asked you to do was to add a variable called y hat to the Porsche price data with the predicted y values. Can somebody tell me how I would do that? So if I have this Porsche price data, how would I add a column? What function would I use to add a column? Mutate, yes. And if I wanted that column to be called y hat, what would I do next? Yeah, y hat equals. And then if I wanted this to be equal to the predicted y values from this my model that I just created, what function in R lets you pull out the predicted or the fitted values? I think somebody said it. Fitted, yeah. So there's this function fitted that will pull out the predicted values from a model. So I can check out that function by typing question mark fitted just to see what it does. It extracts the model fitted values, so exactly what we think it does, and it will extract the fitted values from objects returned by modeling functions. So I can run this. If I just run this here in the console, I'll get a vector of those fitted values. So because there are 30 observations, I'm getting 30 fitted values. And if I want to add that to my data set, I can use the mutate function to do that. And so when I run this here, I see my output, oops. Oh, goodness. I'm going to see my output here in the console, but I haven't actually saved it as anything. I've created this column, and now I can see that that column is created. If I wanted to actually overwrite my Porsche price data set, so instead of having 3 variables, it had 4, what would I do to save this new data set that includes this additional column y hat? Anybody know how to do that? Yes?
You put like whatever you want to call the new data set in front of it with like the arrow button.
Yeah, exactly. So I'm going to call this new data set Porsche price, so it'll be the same. So when I run this, it updates that Porsche price object to now include 4 variables instead of just 3, and now I've got my y hat variable in there. Great. Okay, and now what if I wanted to add another variable called residual with the residuals? What would I do for that? How would I calculate the residuals here? Yeah, price minus y hat, exactly. And now it's going to still update that same object, so now I've got 5 variables in this data set with the 5th one being this residual. And so now I can take a look at this. For example, I could summarize this data. I could look at the average residual, and based on what I just showed you in the previous little application, you should expect that this is going to be 0. So in linear regression, when you fit a linear model, the sum of the residuals, if you added up all those residuals, it's going to be 0. And so when I do that, I get this -3 times 10 to the -15th, which if we round that to any kind of sensible number of digits, it will just be equal to 0. All right, are there any questions about that application exercise? Yes?
I'm getting an error on my mutate saying there's object my model not found.
Oh, so that is because, so I called my model, but if you called it something else, did you save your model as something up here?
Oh, yeah.
Yeah. It's a good question. Does anybody else have questions? All right. Okay, let's then pick up with today's slides. All right, so today we're going to be talking about drawing inference, which basically means that instead of just trying to describe the relationship between data in a single sample, so far we've just been talking about these beta coefficients or these beta hat coefficients, that without any kind of uncertainty associated with them, it's really just describing basically what we're observing in the sample of data that we have. So we're observing basically on average how these variables are related. But if we wanted to sort of talk more about a general population, then we have to start thinking about the uncertainty associated with our particular methods. So last class, you all went and got some magnolia data where, in theory, you measured the length and width of some leaves on the mag quad. And so this is a sample of 30 of those potential measurements that we're going to be working with. And so far we've been talking about the assumptions needed when a simple linear regression model is useful as a summary, a descriptive summary. So without the kind of, without the necessity of kind of drawing inference or being able to talk about what might happen in a different sample. And for that to be true, we've talked about how linearity needs to hold. So because this is a linear measure, if the relationship between x and y is not linear, then it's not going to be a very useful descriptive summary. You could still fit a linear regression model. It just might not be a useful way to describe the data. The residuals have zero mean. So this is actually always true for simple linear regression, and actually for any linear regression model that you're fitting. By default, the average residual, or the sum of the residuals, will be 0. This is just the case based on how that model is fit. So that basically just ensures that this line basically is a good summary. It's not just a random line drawn between these points. And then this final one is one we haven't really talked about yet, but the data points need to be independent. So that basically means that there's not some kind of interdependence that drives the relationship that you're seeing that isn't accounted for somehow. And this one is one that this magnolia data that we're using, we're treating these as independent here, and I'll show you in a second why that might not be a good assumption, because there probably is something different. The way that each of you measured those leaves, kind of depending on what you used. So some of you used your iPhones, and some of you used rulers or tape measures, and that probably breaks this independence assumption. And there's some other, each of you might have a different way of measuring leaves, and so the measurements that you got for your leaves might be more dependent on each other than they are between the different measurements, and so these are different ways that assumption might be violated. But assuming that it's true, then linear regression can be a useful descriptive summary. And within each of your samples, of 30, that should be true. Okay, but what if we wanted to draw inference on another sample? So what does that mean by draw inference? Well, so far we've only been describing our sample. So for example, we've been describing the beta hat 1, the estimated slope of the relationship between two variables. But if we want to extend these claims to like a whole population, we need to have some kind of measure of uncertainty to do that. So for the magnolia data that I just sampled, what are some ways to visualize single continuous variables? Histogram, yeah. So here's a histogram of the 30 observations that I pulled for the length of leaves in centimeters. And another way could be a box plot. And this is a box plot of all of your measurements that you all did. And so you can look at my 30, these little blue dots overlaid over yours. And basically what we're trying to get at is we just have kind of a snapshot. So I just have my 30 observations, and I want to sort of see how that relates to the general population. So if I'm trying to make some kind of inference or draw some conclusions based on my 30 little observations, I need to sort of think about ways to map them back to the whole population, which requires me to think a little bit about the uncertainty in those that I've measured. Okay, so if I wanted to calculate the average leaf length of magnolias just in my sample in R, what function would I use? What function do I use to calculate? Have we used to calculate an average? The mean, yeah. And we can do that with the summarize function. So for example, I could take my magnolia data and calculate the mean of the leaf length variable like this, where set the mean length in this case is 14.8. And the other way to do it that we talked about last week is we could also fit an intercept-only model. So we could also use the LM function, where our y variable here is leaf length, and we just have a 1 on the right side of the equation. And that also gives me this beta hat 0 here, or the intercept in an intercept-only model is the same as the mean. And the reason I'm showing you this is because the LM function will also calculate for you some other quantities that we're interested in when we're thinking about uncertainty. So we get 14.8 in my particular sample. So on average, the leaves in my sample of 30 are 14.8 centimeters. Okay, well, what if I wanted to know the average leaf length of the magnolias on the mag quad? So, no problem. So if I wanted to do that, how could I quantify how much we'd expect the mean to differ from one random sample to another? What measure of spread might you use for that? The standard deviation, right. So the standard deviation of the mean is called the standard error. So this is this measure of uncertainty. The standard error it's a standard deviation of the mean, and it's how much we would expect the sample mean to vary from one random sample to another. So assuming that you're all kind of drawing your data or kind of taking your sample from the same population, so assuming that everybody truly went out to the mag quad and measured randomly some leaves out there, we would expect this we'd expect our sample mean to vary within each of your samples of 30 at sort of the same rate based on this standard error that you could calculate. So in R, you can get this by using the summary function on the model object that you fit with the LM function. So here, I fit an intercept-only model to calculate my mean, and I saved the output as an object called mod. And then I used the summary function on this object, and it output this little table here, which has the estimate, which is, in this case, beta hat 0, which is the same as my mean, and it also has a standard error, which is going to be, in this case, 0.9. Okay, so what I want you to do is go ahead and create a new project from this template here and replace the text in the top code chunk that says insert your Google spreadsheet URL here with the Google spreadsheet URL with your Magnolia data. And a couple things before you do that to make sure this is going to work properly. One, you're going to want to make sure that that your file is shareable. So your Google spreadsheet, you want to make sure that you allow it for anybody with the link to view. So make sure that that is shareable. And then the second thing you're going to want to do to make sure that this will work is make sure that your data is in the first sheet of your spreadsheet. So make sure it's not like in the second or third sheet. And then the third thing is when you run the code after replacing this link, you're going to get this little message that says 1 yes, 2 no in the R console. You're going to type the number 1 and then enter. And it's going to bring you to a web page where it asks you to log into your Google to give it permission to be able to access this sheet. And you want to make sure you check. There's going to be 2 boxes automatically checked. There's a third box that's unchecked. You want to check that box to let R have access to this particular Google sheet. And then you'll click allow and kind of proceed from there. And it should all work. But if for some reason those steps are not working, raise your hand and I'll come help you get it to work. And once you've got your data read in from this Google Sheet, I want you to fit an intercept-only model to calculate the average leaf length in your sample, and then use the summary function on that linear model that you fit, and see if you can find the standard error for the mean length and interpret this value. I'll give you a couple minutes to work on that. And just if your data isn't reading in, go ahead and raise your hand and I will come try to investigate. Yes. Oh yeah, this is right. And then you're gonna copy this, and then you're gonna come over here, and you're gonna paste it in there.
Do we keep it in quotations?
Only two.
Yeah.
Okay, wait. Let me see. Yes, you keep it in quotation, but I think if it's failing, it's possible. Did you check the yeah. Okay, I'm gonna have you do it one more time and do this. And then there's a little box here to check this box. Right? That's okay. And then is this yes? This one? And then this is a little copy.
Yeah.
And then okay, is that enough?
So I got to this point where like I
Yes.
copied the code and it just like got me all
Okay,
this.
yes, I think what happened maybe, let's try one more time, let's make sure we check the little, oops. We're just gonna read off in this form, and do it one more time.
Okay.
Maybe I didn't check
Oh,
this box
yeah,
here.
that's probably what I didn't do.
And then,
Cool, thank you.
so, and let me, I'm gonna show something, so it looks like everyone, a lot of people are having similar problems. Oh, here's the good actually, so hit yes, here's the big one. And then enter.
You know, when you paste
Gonna
the
open this
card,
little
you get
Okay, so if it, oh. Okay, then this is it. So you're gonna hit that, you're gonna type the letter number 1, and then this. It's kind of hard. I probably should have just like shown everyone because it's like hard to describe. You only have to do this one time and then it will work. Okay, there it is. Alright, let me show everybody real quick in case a couple of you are having the same problem. So let me just show you what it will look like on my screen. So let me go to Apex 08. Okay, so when I try to run this, if I put a little sheet here, I'm going to see something like this, where it asks me, it's requesting my Google to access my Google account. Yours might just say like 1 yes, 2 no, or something like that. You have to type the number 1 down here in the selection. I'm going to type 0 just so I can show you what happens when I redo it. And then it's going to take you here where it's going to say choose an account. I'm going to choose my Wake account. And then make sure you check this box down here. And then you'll say continue. And then you'll copy this authorization code. And then come back here and paste it in R. And then you should be able to run it from there. Now, if you've done that and it didn't work for some reason, go ahead and run GS4 auth, so GS4 AUTH with these parentheses, and then hit enter, and then type 0, and it'll force you to go through the process again, but make sure that you check this little box when you go through, and then click continue, copy the code, and it should work from there. All right. Okay. All right. So, is anyone still not working? Okay, I am going to work on a small subset. So we're going to pretend like I have already read in this data. So I'm going to call my data here, well, I can just call it D. I've got it named Magnolia data, but I'll change it to D so we have the same code. So here's my data. Yours should look something like this, where you've got an observation leaf length and leaf width. Let me get rid of this ID so that we have the exact same data. All right, so I've got 30 observations here with a leaf length and leaf width for each of them. If I wanted to calculate the average leaf length, what could I do? If I wanted to do it using an intercept-only model, what function would I use? LM, yeah. And then what would my first argument be? So in this case, the average leaf length in my 30 observations was 15.5. If I wanted to save this little model as an object, what would I do? Yeah, a little arrow. I'm going to call this like mod. And then if I wanted to be able to look at the standard error of that coefficient or of that mean, what function could I use that would give me a table that would include the standard error? Yeah.
Summary mod.
Yeah, exactly. Summary mod. Yeah, so here my mean, in this case this is beta hat 0. That's the same thing because this is an intercept only model. My average leaf length is 15.5 and the standard error is 0.8. So that standard error basically gives me some sense for the kind of variability I would expect in that mean if I were to take some various random samples. Yes?
For some reason I can't find Magnolia data.
Oh, yours should be called D.
Oh, okay.
Did that work? it would be like, yeah. So this object that you read in here would be the. Are there any other questions? Okay. All right, so why are we calculating standard errors? Well, the whole purpose here is to be able to calculate confidence intervals, and also kind of a big learning goal for today is to make sure that we fully understand what a confidence interval is. And so the definition of a confidence interval is here. If we use the same sampling method to select different samples and computed an interval estimate for each sample, we would expect the true population parameter, which in this case is the average leaf length on the mag quad, to fall within the interval estimates 95% of the time. I'm going to restate this a whole bunch of times because confidence intervals are sort of constantly being misinterpreted in our field and beyond. But a couple things to note here is that a confidence interval is not the probability that a value falls within some range, because we're talking about you have already completed your sample. That happened in the past, right? You all went out on the quad and you calculated, you pulled out your rulers or your phones and you got the sample of the data, and now you calculated a standard error, which we're going to use to calculate a confidence interval. That confidence interval exists in the past, and whether or not the true average leaf length on the mag quad, there is a true value for that, right? That's what our beta 0 here, the parameter of interest, is the average leaf length on the mag quad. That number exists. We don't know what it is. It's unknown, but it's a fixed number. And whether that true number falls within your confidence interval, the probability is either 0 or 1, right? So it's not going to be 95 because either that number is in your confidence interval or it is not in your confidence interval. So the 95% that we talk about with confidence intervals, it refers to the sampling method that was used and how often the truth is going to fall in the intervals, with an S, that were calculated using that sampling method. And so I'm going to show you, first of all, we're going to sort of demonstrate that it turns out that the sampling methods that you all used were not totally random. So you all probably didn't sample things exactly the same way. So I'm going to show you the coverage probability, which basically means how likely it was that the sample, that the confidence interval that you all are going to calculate contains the truth. That's the kind of coverage probability. If each of you really truly did a random sample where you all calculated your leaf lengths and leaf widths exactly the same way, we would expect 95% of the intervals that you all are going to calculate to contain the true average leaf length on the mag quad. Now, if they didn't, then we're going to expect a lower percentage. And so I'm going to show you basically how we're going to do it with your data. And then we'll do it in a theoretically where I basically simulate as if we were to have randomly sampled this accurately, and we'll show kind of how that would compare. Okay, so how do we calculate a confidence interval? Well, the big picture is that you take the mean, here x bar, or beta hat 0, and you add or subtract, depending on if you're calculating the upper bound or a lower bound, t star, so some critical value that comes from a t distribution, and we'll talk about why in just a second, times the standard error of that x bar value that we just calculated. And so this t star is a critical value for the t with n-1 degrees of freedom density curve that's used to obtain the desired confidence level. So, for example, often we want a 95% confidence level. And so for that, we would find basically the 2.5th and the 97.5th percentiles of the t distribution, or the quantiles of the t distribution. We'd find out what those values are, and then we can use those to calculate the 95% confidence interval for that. So I'm going to do a quick demo where I try to show you, to motivate why we're using a t distribution to get these critical values, using the same kind of example that we just did with the Magnolia data, and then we'll come back and you'll calculate your confidence intervals yourself. So I've made this simulation, and the reason why I've made this simulation is because I know that this is going to be truly random because I've simulated it to be so. And so what I've done here is I've created this variable nsamp, which is the number that each person in my simulation is going to sample. So I'm going to, each little individual in my simulation is going to sample 30 leaves. And then I'm going to simulate this 10,000 times. So I'm going to send like 10,000 little people out into my pretend sampling land to calculate the leaf length. And then I'm going to use this mean and standard deviation. We can check. So I've actually pulled in all of your data from the full Magnolia data here. And I can actually check what the standard deviation is across this whole sample. And so, for example, I could, I can summarize the standard deviation of leaf length here. And so this is the standard deviation that each of you would get if you were to run this. And then I can take basically the average of that. So the average standard deviation is about 3.3. So I could plug that in here. 3.03 rather, so we'll just do 3. So essentially what I'm saying is that the leaf length is going to have an average of 15 centimeters with a standard deviation of 3. And so I'm going to simulate this data a whole bunch of times. And so I can take a look at what that looks like. And so, for example, these are 30 observations from the first person that took a sample, and I've done this a whole bunch of times so I can get a whole bunch of these samples. And the reason I'm doing this is so that I can show you kind of why we're using a t-distribution to be able to get these statistics. It's basically shorthand so we don't have to do this simulation every time. We know that these means, so there's something called the central limit theorem, which is a nice theorem in statistics, that tells us that when you're taking an average, in the limit, an average is going to be normally distributed. So if we wanted to know basically how far off we would be on any given sample, we can use these distributional assumptions to allow us to do that. So here, I've taken the average here for each of these means, and I've subtracted. So I've basically taken here. I'm getting the distribution of the statistic that would be like the mean minus the true mean divided by the standard error here. And I'm expecting that this thing is going to be normally distributed or t-distributed in small samples. And so to prove that to myself here, I am going to draw this distribution where in green I show what it would be for a normal distribution, and in red I show a t-distribution. And here I had 30. I don't know if you remember from like stat class. As your sample size increases, your t-distribution is going to go towards your normal distribution, so it'll be similar to your normal distribution. So the reason why these lines are so close to each other is because my sample size was 30. And these lines here basically show the 95th or the 97.5th and the 2.5th, the critical values that would say that 95% of my data falls in between these lines. So I could change this to, for example, have a much smaller sample size, and we could see kind of a starker difference between my green line and my red line. So the reason why a t-distribution is nice is because it has a little bit of fatter tails, which better represents the data when you have small samples. So you see the red kind of follows right along that histogram, whereas the green is a little bit too low here. So that's why we use a t-distribution for those critical values. And so the way that you actually get those critical values in R is using this QT function, which is like the quantile of the t-distribution. And so for this top one here, the quantile, it's going to be the 0.25 quantile, and the degrees of freedom is going to be the sample size that you have. So in this case, my sample size was 5 minus 1, so the degrees of freedom is 4. And then lower tail equals false is just because by default, it's going to pick this one down here, and I want to have this one up here. And so it tells me that my critical value here is 2.77. If I didn't have that lower tail equals false, by default, it would just give me this lower critical value. So it would just be, because the t-distribution is symmetric, it would just be the negative version of that. So the reason I do lower tail equals false is because I want the positive version. Do you feel motivated to use a t-distribution in your confidence intervals now? Did this give some sort of sense of why we're doing this? Maybe. Okay. I feel like this is a little hard sometimes for it to sink in, but hopefully it's giving a little sense as to why we might do that. So coming back to R, if we fit our model, our intercept-only model, we use the summary function to get our mean. So in this case, 4.8, and our standard error, in this case, 0.912. I can use that same QT function, the quantile of the t-distribution, to get the 0.0225 quantile. My degrees of freedom is going to be the number of rows in my data minus 1, so 29 in this case, because there are 30 rows in this data minus 1. And then lower tail equals false, I get this critical value of 2.04. So why am I using 0.025 as the quantile here? Yes, I'm calculating a 95% confidence interval, so I want to have 95% in between my two values. So it's a two-sided confidence interval, and so I'm going to have 2.5% on the upper side and 2.5% on the lower side, so that's why I use the 0.025, because 0.025 plus 0.025 equals 0.05. If I wanted to do a 90% confidence interval, what do you think I would put for this value? Yeah, exactly, 0.05. And why do I use the lower tail equals false? What would happen if I didn't have that? Exactly, it would give me, yeah, if I didn't have the lower tail equals false, it would give me like the other side, which would just, it would be the same value but negative, because it's going to give me the first, the default in R is to give the first quantile, and so if I want it to be the second, I need to use this. So I can use this. This is going to be my t star value, like the critical value from the t distribution. And I can take my mean, so 14.827, and then add t star times my standard error. And what would this value, what is this 16.7? What does that correspond to? What is it? Yes. Yes, exactly. The upper bound of my 95% confidence interval. And then I can take my mean and subtract t star times the standard error, and I would get 13. What is this 13 then?
Lower bound.
Exactly, the lower bound of my confidence interval. And so it turns out, I think it's good to know how to do this by hand in R, but it turns out there's actually a function that can do this called confint. And so if you apply this function to the model object, so this object from the LM function here, we get the same thing. So we get a lower bound of 13 and an upper bound of 16.7. So the same thing that I got when I did it by hand. Okay, so how would you interpret this value here in the context of the Magnolia data? What does it mean that my confidence interval goes from 13 to 16.7?
95% of the data falls within this interval.
So that's a very common definition, but it's actually not quite the right definition, because it doesn't mean that 95% of the leaves outside fall between 13 and 16.7. Yes.
It's that 95% confident that the true value, the true mean is between those two numbers.
That's very close, but it's even still, the word confident, I think, gets used often in this case, because what does it mean to be confident? But even that is a little bit off, because the truth is either inside this or not. That's like a fixed value. The true value out there, like let's say the true value is 15. There's a 100% chance that 15 falls between 13 and 16.7, because we just know that 15 is in between these two numbers. So the chance that it's in between these numbers is isn't quite. What this is saying is that basically, if we were to do this process many, many times, every time, and what you're about to do this process yourself on your own data, every time you would get a different confidence interval. And 95% of those intervals, should this method have been what we expected it, should it have really been a random process, 95% of those intervals would contain the true value, which let's say it's 15, would contain the true value of the average leaf length. So it has to do more with the process than with these particular values. But I don't mean to, those are both very common answers, and so I'm glad that you said them because I think that is a very common misinterpretation, and in fact I think it's mistaught a lot of times. But the actual definition of a confidence interval has to do with the sampling method. So if we used the same sampling method to select different samples and computed an interval estimate for each of them, we would expect the true population parameter to fall within the interval estimates, so with an S. So not that interval estimate, but all of the interval estimates 95% of the time, or whatever percent kind of that you've set. So what I want you to do now is go ahead and go back to that application exercise, calculate the T star value for your confidence interval, so for your Magnolia data, and then calculate the confidence interval both by hand using that T star value, and then also calculate it using the confint function and sort of see how those compare, and then see if you can interpret this value. And then we're going to do the same thing, but I'm going to do it across all of the data sets so you can see how that would compare. Yes? Oh, here, let me see. This is your, oh, see, it's because it's in sheet 2. It needs to be in the first sheet. Let's try this. You're welcome. Yes. Oh, yeah. So that now you have to just run this here. Yep. You're welcome. Oh, yeah. So this is, so the instead of D, you would want to put the name of your variable here. Which in your case,
Yeah, I know, I tried, but.
yeah, so it's because your variable name actually, it will be a little easier if you keep the variable name the same as what I had put it without the centimeter, without that. Because that's just, it's possible to do it like that, but you just have to deal with the space. So if you do it like this, now the variable names should be just leaf length, which is easier to deal with. And now you can do that here at the leaf underscore. There you go. You're fine. Yes.
Oh, there. Yeah, okay. That's fine. Yeah, yeah, yeah.
Do you have a question? Oh, you're allowed. Okay. I I'm going to start doing this. So I'm going to use, let's see. Oops. Let's see here. All right, so I have this little data set here with a, and now my mean is a little different in this particular data set. I've got an average of 22 and a standard error of 0.58. If I wanted to calculate my t-star value for this data set that has 30 observations, what function would I use if I want to do this by hand? I want to calculate this critical value for my confidence interval. QT, and does anyone know what the Q stands for in QT? Quantile, yeah, it's the quantile, the t-distribution, exactly. And which quantile are we trying to calculate? The 0.025, which corresponds to a 95% confidence interval. And what would I put as my degrees of freedom here if I had 30 observations? 29, exactly. So I get this t-star value. Oh, and I left out one thing. I ended up with negative 2.04. If I wanted that to be a positive number, what would I do? Lower dot tail equals false, and now it'll be a positive number. It's not terribly important. It basically just means you're flipping your upper and lower bound if you use the negative or the positive value, but it's easier for me to conceptualize when I think about the positive value. Okay, so my x bar, my mean here is this, in my case, is this 22.4667, and my standard error is this 0.58. Yours is going to be different depending on the data that you collected. If I wanted to calculate the upper bound of my confidence interval, what would the equation be that I use? Yes?
X bar plus T star times the standard error.
Exactly. And so I ended up with 23.66. And if I wanted to calculate the lower bound, what would that be?
Same thing but minus.
Yeah, same thing but minus. Exactly, and I get 21.27. And what is another way I could get these values using this output from this model that I fed up here? Confident, yep, confident mod. And it gives me the same 21.27 and 23. Okay, so now what do these mean? Well, I wanted to show you, so I have pulled in here all of your observations. We ended up with 869 measurements of leaves. And I can take these measurements here and I can show you basically, I can show you how that compares we can basically calculate the coverage probability or how likely we are to have the true value within those values should this have been a random sample. So if I take this full Magnolia data and I group by ID, I've created a unique ID for each of you that submitted your data. And the way, just to show you how I've done this, I basically took, this is the spreadsheet where you submitted your data via that Google form. And so I took that spreadsheet and read it in. And then I created this function that basically will read each of those sheets. And then I'm binding all of those rows together. This function just makes a little ID for each of you, so you can see a little bit of the R code that did that. Okay, so I'm going to group by ID, and I'm going to summarize to calculate. First, I can calculate like the mean in each of these. So the mean leaf length. And let's start by just looking at that. So I end up with 29 observations here. So the reason why this is not, there were like 40-some people that submitted their data, but some of those, like the sheet maybe wasn't in the first sheet, and some of those I didn't have access to, so that's why. So anyways, 29 of them I was able to access. So of those 29, these are the different averages, and there is some big variability. So I think we're probably not going to see, it's unlikely that we're going to see good coverage here. For example, I think maybe some people accidentally used inches instead of centimeters, because an average of 6 centimeters would be like kind of small for a magnolia leaf. So some individual people maybe mixed that up, although it's possible that maybe there's like a baby tree somewhere that everybody sampled from the baby tree, which would suggest this wasn't a random sample. So in any case, I can calculate the mean of each of those, and I can calculate the standard error. So that's just going to be the standard deviation divided by the square root of n, which in this case is 30. And I can use that same t-star value because these are all the same. These all had 30 observations. So the upper bound is going to be that mean plus t-star times the standard error. The lower bound would be the mean minus t-star times the standard error. So I can, and this is a little bit hard to see, so maybe first what we can do is plot these and see how they look. So I'm going to plot this data. And so we're going to plot from the lower bound to the upper bound. And so this will show you, let me just remove this here. So this shows you all of the different confidence intervals that each of you would have calculated. And as you can see, there's a really wide range. And it's unlikely that just from looking at this, I'm going to guess that this wasn't a totally random process. And the way I can tell that is because basically these confidence intervals don't overlap like you would expect them to if they had really come from the same distribution. But I think this is still instructive for sort of thinking about what a confidence interval is. And so what I'm going to do now is I'm going to add a line with the truth. So let's pretend like the true value for the average leaf length of a magnolia is 15 centimeters. And so in theory, the coverage probability, or the actual confidence interval, the probability here for these samples would be the number of these confidence intervals that include the truth. So we're calling these 95% confidence intervals, but it turns out for this particular sampling process, these are not 95% confidence intervals. There's something much less. We can calculate the coverage probability as just summarizing. It's going to be the total, the proportion that include the truth. And so this would be like where the lower bound is less than 15 and the upper bound is greater than 15. And so in this case, we had 27% of the time, this is like the coverage, 27% of these confidence intervals contain the truth. So that would mean that these were actually 27% confidence intervals, not 95% confidence intervals for the sampling process that took place here, because the sampling process was not actually random. So what I'm trying to drive home is that here, in this, did anybody have a confidence interval that did not contain 15? Andrew. Okay, great. So what was your confidence interval?
It was 12.8 to 14.9.
Oh, that was close. But okay, 12.8 to 14.9. So that's like, maybe it's this one right here. That might be you. Okay, so what is the probability that 15 is in your confidence interval? It's 0, yes. So this is sort of to try to drive home the point that a lot of times when people interpret confidence intervals, they try to say that it's the probability that the true value is in that range. But it's not, because that probability is either 0 or 1. Either the truth is in that range or it isn't. What the 95% means is that if this was a random process, if we did this same sampling procedure 100 times, we would expect 95 of them to have the truth. I'm going to show you in just a second. I'm going to generate a random process that's actually random, because this one maybe wasn't exactly random, and we should see that about 95% of them contain the truth. Did anybody have a confidence interval that contained 15? You did? What was yours, Christopher?
14.7 to 17.79.
Yeah, 14.7 to 17.79. So like maybe that may have been like this one maybe, or maybe this one. No, this one probably, because it's less than 18. So what would be the probability that 15 was in that confidence interval? 1. Yes, it's 100%. So what I'm trying to sort of demonstrate is that the 95% confidence, the relationship between that and the probability of the truth being in the interval, like those are not related. The truth is either in it or it isn't. The 95% refers to the sampling process. So this one, these turned out only 28% of these actually had the truth in them, and that has a little bit to do with our sampling procedure probably not actually being truly random. So what I'm going to do is I'm going to go back to my pretend data here where my sampling procedure really is random. Whoop. And, oh dear, where did that just go? Here we go. And so if I pull this really, truly random data in, and I'm going to do this same, I'll change this to ID so we can use the same code. So if I take this same code here, but instead of using the full Magnolia data, I'll use my simulated Magnolia data. And I can calculate the coverage here. Uh-oh, that's way lower than I would have expected. Let me see. Oh, let's see. This is, what are we trying to do? Oh, this is 5. So we're going to change this NSAMP to 30 so that it matches what you all did here. So our coverage now is 95%. So that means that when we actually truly had a random process, we found that 95% of the intervals contained the truth. And let's show, let me show that here with the plot, because it's a little bit easier to see when you visualize it, I think. So if we look at this plot, so this is just of the simulated data now. So now these are my confidence intervals of my simulated data. And you'll notice here that basically we can highlight which ones fall outside, but here I've got 100 observations or 100 samples. 5 of them did not, on average, 5 of them didn't include the mean, but most of them did. So for any one of these confidence intervals, the probability of including the mean, it's sort of irrelevant. It either does or it doesn't include the mean. What the 95% refers to is that across a whole bunch of samples, what proportion of them are going to include the truth? Does that sound? Yeah. Great. Okay. All right. So now we've got like 5 more minutes. I'll start talking about this, and then we'll pick this back up at the beginning of class on Tuesday, where basically we do have 4 minutes. Okay. So now I'm going to introduce the other variable that you all collected, the width of the magnolia leaves. And so now we're looking at the relationship between 2 variables, the length and the width. And this is in my full sample. What this tells me right here is that one person, I think, accidentally flipped the length and the width, or they put in their first column, they put the width instead of the length. So we have 30 observations that look really different than all the other ones. These are mine in blue here. And so if I wanted to know the relationship between leaf length and leaf width for magnolias in the mag quad, and I wanted to quantify how much we'd expect the slope to differ from one random sample to another, it would be the same process. So we would use some measure of uncertainty. We could use the standard error of the slope. And the standard error is going to be how much we would expect beta hat 1 to vary from one random sample to another. So the same methods that we just used for the mean can extend to any of those parameters that we're estimating. And so now instead of fitting an intercept-only model, I'm going to fit a model that predicts the width from the length And now I have two estimates in this summary. This is my beta hat 0, or my intercept, so in this case it's 2. And this is my beta hat 1, or the slope, and it's about 0.3. And then these are my two standard errors, the standard error for beta hat 0 and the standard error for beta hat 1. And so we need some test statistic that incorporates both beta hat 1 and the standard error. And so we can use the t statistic to do that, which is just going to be that beta hat 1 divided by the standard error of beta hat 1. And so that is also in this output. So right here we've got this t statistic here, this 3.41. And what that means is that you would, this needs to be 3.41. Hold on. I reran with the new data. Let me just change that real quick so we don't get confused. It should be 3.41. Okay, let me just refresh that. All right, so what this means is that beta hat 1 is more than 3.41 standard errors above a slope of 0. And so this t-value gives us some sense for the relationship between x and y in terms of standard error units, which sort of lets you map it back to the overall population. And so the way that we can tell which values of this statistic are worth paying attention to are via these confidence intervals or p-values or hypothesis tests, which we will pick up next class and talk about that.